All right, moving along. Okay, so these numbers give us a very poor signal-to-noise ratio at the physical point. However, it's much alleviated if we go to unphysical pion masses or unphysical quark masses. And so back in the day of Lattice QCD, people would do calculations away from physical pion mass because inverting the Dirac operator became very costly. Nowadays, that's not such a big hurdle. However, if you're talking about nucleons, we still have to go to unphysical pion masses because of the signal-to-noise problem. There are other reasons to go at unphysical pion masses. It helps with it in extrapolations, etc. But the main reason these days is due to the signal-to-noise problem. So what happens at unphysical pion mass? So we know about chiral symmetry breaking, hopefully, and we know that in the limit that the quark masses go to zero, the pion masses become exact Goldstone bosons related to the spontaneously broken chiral symmetry, and therefore the pion mass is also zero at that point. This is the chiral limit. And due to chiral symmetry breaking, because the pion is a boson, its mass comes into the Lagrangian as an m pi squared, whereas the quark mass, the quarks come in as an mq because they're fermions. And we know that the pion mass has to be proportional in some way to the quark mass so that this property is obeyed. So the pion mass squared is proportional to the quark mass. And you can figure out the constant of proportionality by just plugging in some numbers, but it's of order the GeV. The baryon mass, on the other hand, does not get most of its mass due to the quarks. It has a non-zero mass even in the chiral limit. So this is the chiral limit mass because it's not associated, it's not a Goldstone boson. And then it has some MQ dependence after that. But these quark masses are much, much smaller than the mass in the chiral limit, which is, again, of order a GeV. Of order, it's more like 800 MeV, but it's still quite large. And so we can neglect this quark mass dependence to leading order. So if we look at the thing we had in the exponent for the signal to noise, that was MB minus 3 halves. Let's be concrete here. Let's stick to the nucleon so that our mesons are always pions, right? Then this guy goes like m naught minus some constant times root mq. So this guy has no quark mass dependence. That would be higher order. And then the pion mass term is proportional to the square root of mq. So as we raise the quark mass, m naught stays constant, but this term grows. And therefore, the difference between them will go down. And therefore, the signal to noise exponentially increases. So this is why we work at heavy quark mass in nuclear physics. You can ask, is there a limit to this? Can we raise the quark mass to the point where we have an exponentially growing signal to noise? The answer is, of course, no, because nothing is easy. It's the no free lunch theorem. So we can go to the infinitely heavy quark limit, where there's no chiral symmetry breaking. And in that case, in heavy quark physics, the quarks act like static sources, and you have Coulomb-like interaction fields between them. So roughly, the masses of the particles scale with the number of quarks in the system. That's a nucleon again. Oh, yes. So your nucleon looks like 3 heavy static quarks, and your meson looks like 2 or 1 heavy static quark and 1 heavy static antiquark, and so their masses just add. And in this limit, the argument in the exponent goes to 0, so the exponential time dependence goes away, and the signal to noise is just proportional to the root of the number of configurations. And this argument, I'm out of space, that's okay, is related to a triangle inequality. So this is a hard limit. The mass, 3 times the mass of the pion can never be larger than twice the mass of the nucleon through just a simple triangle inequality argument. So if you remember the 2 terms from the variance here way back when, these 2 guys, sigma squared must always be positive, which means that the second term always has to be smaller than the first term. And that is the triangle inequality, which says that if you have a positive definite number that you're summing over some number of samples, that's always going to be larger than a number that can fluctuate between positive and negative that you then sum over configurations, because some of those are going to cancel, or at least some portion of that is going to cancel. And so the positive definite operator always is larger than the non-positive definite operator. And because remember, these guys scale like an e to the minus mt, if the positive definite one is always larger, that means that the mass in the exponent is always smaller. And so this gives an inequality that mn is always greater than or equal to 3/2 m pi. And so the best you can ever do with your signal to noise is to have it be time independent. You can't have it be exponentially growing. And so with that, we can go to the next question, and I'll stop this video.